We all run on energy, right? But have you ever stopped to think about what would happen if the key that unlocks that energy just stopped working? Today, we're going to take a journey, a trip deep inside our cells, to really understand the story of type 2 diabetes. We'll see how a system that's supposed to be perfect can slowly and silently start to fail. Let's dive in.
So I want you to imagine something. Picture every single cell in your body with a tiny locked door. And behind that door, that's the power plant. The fuel it needs to run is sugar, glucose. But to get that fuel inside, you need a very, very specific key. So the big question becomes, what happens when that key starts to fail?
And that question brings us to the absolute hero of our story, the one essential key that powers the whole operation. So that key? It's a hormone called insulin. When you eat a meal, sugar from your food enters your bloodstream. Your pancreas senses this and releases insulin, which travels all over your body like a master key. Its main job, its whole purpose, is to get that sugar out of your blood and into your cells, where it can be used for energy. Simple as that.
And this is a really, really important point to get. Insulin isn't the energy itself. It doesn't carry the fuel. It just opens the door so the fuel can get inside. Without this key, all that valuable energy is just locked out, stuck floating around in your blood where it can't do any good.
So how is this all supposed to work? I mean, when everything's running smoothly, it's actually an incredibly elegant and, flawless system.
Okay, let's walk through it step by step. First, you eat, and glucose hits your bloodstream. Check. Your pancreas releases insulin, our key. That key travels to a cell and finds its specific receptor. That's the lock. When the key clicks into the lock, it sends a signal to open a special door, a transporter called GLUT4. Then, whoosh, glucose rushes in, the cell gets its energy, and your blood sugar goes right back to normal. See? It's a beautiful thing.
Now don't get hung up on all the complicated words on this diagram. The real takeaway here is just to see the incredible complexity that's happening behind our simple key and lock story. When insulin binds to the outside of that cell, it's not just one click. It sets off a whole chain reaction, like a line of dominoes falling, all these signals you see mapped out here. And all of that just to tell that one little GLUT4 door to open up. It's this beautiful, intricate dance happening millions of times a day inside you.
But what happens when something goes wrong with this flawless system? The key is still there, but the lock starts to get sticky. It begins to jam, and this, right here, is the very beginning of what we call insulin resistance.
So insulin resistance, what that really means is that your cells, especially in your muscles and liver, start to, ignore insulin's signal. The key is still floating around, it's trying to do its job, but when it gets to the lock, the mechanism is stiff. The signal to open the door is weak, and sometimes the cell just doesn't hear it at all.
Okay, look at this side by side. It's like a tale of two cells. On the left, you've got your healthy cell. The key works perfectly, the door swings open, and all that glucose gets inside. Happy days. But on the right, you've got an insulin-resistant cell. The key is kind of bent, the lock is all jammed up, and the glucose, it's trapped outside, just building up in the bloodstream.
So, the big question is, what's actually jamming the lock? Well, one of the main culprits is the buildup of fat in places it really shouldn't be, like inside your actual muscle and liver cells. This is what's called ectopic fat. This misplaced fat releases tiny particles that directly interfere with that whole domino chain reaction we saw earlier. It's literally gumming up the works from the inside out.
And this diagram shows us exactly where that breakdown is happening. If you look closely, you'll see the term intracellular lipid. That's just a fancy way of saying fat inside the cell. And as you can see right here, when that fat builds up, it basically throws a wrench into the signaling pathway, stopping the message from ever getting to the GLUT4 door. And the result of that? Insulin resistance. Now here's the thing. Your body is smart. It's no dummy. It realizes the doors aren't opening and that sugar levels are staying too high. So what does it do? It puts all the pressure on the key maker, the pancreas. The pancreas goes into full-on crisis mode. Its logic is basically brute force. It's like, okay, if one key won't turn the lock, maybe 100 keys all rattling the door at once will get the job done. So it starts working overtime, flooding your system with an absolute army of insulin keys to try and force those doors open.
This state of having chronically high levels of insulin has a name, hyperinsulinemia. And this is so important to understand. For years, we're talking maybe 10 or even 15 years, this strategy actually works. The flood of extra insulin manages to keep blood sugar levels normal.
But the whole time, silently, the system is under incredible strain. And the real problem, the jammed locks, is just getting worse.
I mean, you can probably guess what's coming. The pancreas is working around the clock, pumping out way more insulin than it was ever designed to. And just like any factory that's pushed too hard for too long, it just can't keep up that frantic pace forever. The strain starts to take a serious toll.
So what happens to the whole system when the keymaker, the factory itself, simply gets exhausted and can't keep up with the overwhelming demand anymore? This is the tipping point. After years and years of overcompensating, the one part of the system that was working the hardest finally begins to fail.
Think of the beta cells as the little workers on the factory floor inside the pancreas. After years of working non-stop triple overtime shifts, they start to burn out. They get exhausted, they get damaged, and the factory's production line just grinds to a halt. It simply can't churn out the massive number of keys needed anymore.
This table really just summarizes the entire journey perfectly. Look, first, you're healthy. Insulin is normal, blood sugar is normal. Then, you enter insulin resistance. Notice this. Insulin levels are high because they're compensating, but your blood sugar still looks normal. That's that long, silent phase. And then, finally, the system fails. The pancreas is exhausted, insulin levels drop, and with not enough keys for all those jammed locks, blood sugar has nowhere to go but up. And that is type 2 diabetes.
So this is where our cellular story ends up. It's a double whammy. You've got cells that won't listen to insulin signal, and a pancreas that can no longer shout loud enough to be heard. The glucose is locked out, it's trapped in the blood, and that leads to all the problems that come with chronic high blood sugar.
So yeah, the system is broken. But here's the most important part. The story does not have to end here. Understanding this whole process from the very first sticky lock to the exhausted keymaker is the most powerful tool you have. It shows us that this is a slow-motion breakdown, not something that happens overnight. And because it's a process, it means there are chances to step in. Knowing how the system breaks gives us clues on how we might be able to fix it.